captain of each team, please introduce your members from the reporter, opponent, and the beginning.
Okay, so I'm the captain of Ridiculous, and my name is Henry, and this is Johnson from and this is
Hi, we're Team Maya Haha, and this is Martin Lin, Brian Lee, and this is Brian Wang, and this is Ray Tak, and I'm Zoe Chi.
I'm captain of Excelsior, and I am Lin Xuanqi. This is Su Batong, this is Zheng Zongyang, this is Liu Helong, and this is Jing Guoquan. Thank you.
Okay, the opponent, please choose the program to change.
Problem number 7.
Number 7.
Reject.
Reject.
Problem number 1.
Number 1.
Reject.
Okay, reject. We choose another in 1 minute.
Number 13, spaghetti.
Number 17. Okay, the reporter has 5 minutes to prepare. The opponent will
Greetings, I'm Shehan Kui from Ridiculous, and I'm going to present the number 13 spaghetti accelerator. And now it's the outline of my presentation. And it's a problem statement. When the speed of spaghetti is pushed into the pen tube, small debris of spaghetti may be ejected from the other end of the tube at its rising high speed. So here are some key questions: the cause of the phenomenon and the mechanism behind the ejecting speed, and the tube effect on the phenomenon. Now it's our observation video. As you can see, spaghetti will bend due to the force exerted by the tube. So we need to find the force, the relationship between the force and the length. So we use buckling to analyze this phenomenon. And the little r means the radius of spaghetti, and the big L means the natural length of spaghetti. The E means Young's modulus, and I means the second moment of area. And we can get an equation that force will proportional to reciprocal length squared. And now it's our experimental setup. By pushing a spaghetti with a Pascal, we can record a minimum force to break the spaghetti. Now we can calculate a constant dr. And now it is our data analysis. And as you can see, when the length is long, they have a linear correlation. But when the length comes small, there are high deviation. And we can hypothesize that under small length, buckling is not present. And we will discuss about that later. But we still can use the linear correlation to calculate the EI value. But it doesn't explain the whole picture. So let's come to my second theory. It's called fracture. And the fracture is the strength of a material is affected by internal defects such as crack, and the size distribution are random. So after reaching a stretch required to crack propagation, a trend fracture occurs. So we can hypothesize that the stretch is a possibility function because the defects are random. And we need to use our data to simulate the M equals to Weber modulus. And now is our data. And because we need to find a minimum force to break the spaghetti, so we need to pick the smaller one between these two equations. And it can explain the error bar earlier as a probability. Probability function is a characteristic of fracture. And the green line means fracture, and the blue line means buckling. Then we found the intersection is the point of the fracture. And we fit our experimental data. We can find the M equals to 1.1. And we successfully determined the mechanism behind the spaghetti breaking. And if your L is shorter than 8.62 at this point, and you will present fracture. And if it's longer, you present buckling. Now it's my nodule of stress function. And under two cases, we calculate the different stress function in different cases. And this is some physical. And now this is the linear elastic theory. And we use the strain energy density to calculate the total potential energy. And we use the total potential energy equals to kinetic energy to get the equation of velocity. And we will devise this theory later. And now it's come to our experiment 2. It's the humidity effect. And these are initial condition of accelerator. Use 5 cm curvature and the 2R thickness, 60 degrees, and 8 cm natural length. And we soak the spaghetti in the water for 10 seconds, then push it into accelerator by Lego, and compare with the dry spaghetti by speed and the length of debris. And now it's our methodology. And we use horizontal position motion to calculate the initial velocity. And we use Lego to push the spaghetti into a bend tube. And now it's our compression. And as you can see, the soaked spaghetti has a higher speed. And this is because when the ejection length and the natural length are the same, and lateral length is ACM, and the ejection length they are the same, the E value of the soaked spaghetti decrease. E decrease, so causing the slight decrease in speed. Now it's our experiment 3. And we use the radius of curvature as an independent variable. And we use 3D print tube with a different radius of curvature. And now it's our experimental video. And now it's my data analysis. And we discuss the fact about the radius of curvature on speed and ejection length. And now this is data. And as you can see, the curvature increase, the velocity will decrease. And there are linear correlation between the radiance of curvature and the ejection length. And this is assessment of success rate. And as you can see, when the radiance of curvature is going to 7 or 8 cm, the increased ejection length causes a lack of energy. So it will stuck in the band 2. And as the error bar from our experiment, we can see that 4 cm is most stable. So we will use 4 cm to do our next experiment. And now, according to our theory, we draw this picture. And according to our theory, our velocity will proportional to square roots of reciprocal error prong. But it has an intercept. So this is because the energy loss from surface pressure. And it provides a boundary condition of this picture. Now, so experiment 4, we will talk about the tube thickness. And we use the thickness to be the independent variable. Now it's our experimental videos. Okay, now is the data analysis. And as you can see, when the thickness increases, the velocity will decrease. And why they are decreased? Because the influence blocking is decreasing speed. And this is because the fracture is an instantaneous energy release process, and the blocking is a slow deformation process. So the energy fracture contains more energy than blocking. And what happened with this point? This is because the inner wall of the tube doesn't have enough stress to make the spaghetti to go to fracture. So it will stuck in tube. Now this is our theoretical relation. And as you can see, this is our theory. And we drew this picture too. And it also have an intercept. So we can hypothesize that they have a consistent velocity loss due to the accelerator. And we compare the width and the curvature between these squares. And the decreasing slope is due to the buckling decreasing energy. And I told you before later, the energy in the fracture is more than buckling. Now if I note you, there's a collaboration between the speed and the square roots of reciprocal error prong. And radiance of curvature and the width of the accelerator are highly facilitated. Correlation between the length of ejection debris and currents of blocking will lead to a crucial decline in the ejection speed. And the inner walls of spaghetti cannot push enough stress to spaghetti because pressure, the spaghetti will start into. And now is my experiment 5. And we use these different natural lengths to do this experiment. And now is my data analysis. And as you can see, the natural length change, the ejection length doesn't change so much. So compared to the accelerator radiance of curvature, the ejection length has a little correlation with the natural length. So, according to our theory, if error prong is consist, the view will proportional to this parameter. And now this is the result of velocity. As you can see, the minimum force to break the spaghetti is dependent on the length. So the length decrease, the velocity will decrease. And we draw this picture according to our theory. And there are some deviation in 4 cm, and this is because 4 cm is hard to get in the accelerator. And now is our brief summary. And the second and third experiment, we verify the same natural length v will proportional to square roots of reciprocal error prong. And when to multiply an A, it means the energy conversion due to blocking. And the intercept suggests it consists of velocity loss. And error prong is a characteristic of accelerator influenced through geometry by ratio and the width. And we need to consider the velocity loss combined with the buckling explained when the boundary condition occurs. Now so experiment 6, curve angle. With different angles do this experiment. And now our data analysis. And as you can see, there are no clear correlation between the angle and the velocity and the ejection length. So we can trust that G is not consistent with different angles. And now is the normalization. We compare our 4 experiments and know that the width has a great impact on the length of eject debris. And the ejection speed is primarily affected by the radiance of curvature. So this is our accelerator final test. According to our experiment, we designed an accelerator that can generate a maximum ejection speed, and it has those conditions. And we also use 8 cm natural length to push it. This is experimental video. And now to my data analysis. According to our experiment, the ejection speed is faster than any previous experiment. But well, the ejection length is shorter than in any experiment. So we verified again the velocity and the ejection length of debris are negatively correlate. And now to my conclusion. The pressure maximum of spaghetti depends on its length. So when the length is longer than 8.62 cm, it presents buckling, and when it's shorter, it presents fracture. And the ejection speed is currently affected by the radiance of curvature. And the shorter the radiance of curvature, the faster speed. And we show it in normalization. And the length of ejected debris is mainly influenced by the accelerator's width and the radiance of curvature. The greater width and the longer radiance of curvature both result in a longer ejected debris. And 4, the greater humidity, the smaller the E value of the spaghetti. And this is because the air pump is consistent. According to our experiment, the air pump is consistent, and we use the same natural length. So we can hypothesize its E to make this result. And according to our revised theory, this equation, we can find the relationship between the speed and the natural length and the ejection length under different conditions. And this is my report. Thank you.
The opponent, you have 2 minutes to ask a question.
So, have you, in your experiment, have you considered the realized side, like the initial side that you push the spaghetti?
Oh, I consider.
Oh, okay, I think we can discuss it later. And have you considered the energy loss?
Yeah, I consider the energy loss. It's the G represent to the velocity loss.
And do you consider the force to push the accelerator?
Oh, because I'm using Lego to push the spaghetti, so and it keep the very slow velocity to push the spaghetti, so we can ignore this effect.
Excuse me, one second.
Oh, I see a video. Yes. We use Lego to push it in a very extremely slow velocity, so we can ignore this effect.
So, you have standardized every time the velocity pushing?
Yes.
Okay. And can you turn to page 41?
31?
41.
41.
Yes. Can you briefly talk about the conclusion of this page?
Well, this is our accelerator final test, and we just designed this accelerator can have a fast velocity. So this is our one of design. So according to our experiment, we designed this velocity can have a higher speed, higher ejection speed.
With what?
This curvature 13 and 1.5 R and 75 degrees.
Also, with
Okay, 3 minutes for the opponent to defend. Okay, the opponent, please take the floor. You have at most 4 minutes to present the final divider discussion with 40 minutes in total.
Hello everyone, I'm opponent from Maya Haha and my English tag. So this problem statement is about bending spaghetti into a tube, and it will have a small device that has a high speed to eject it out. And the point of focus from the reporter is the cause of this phenomenon and the mechanism behind it. So the observation, they have observed the buckling, the fracture, and the humidity. And the experiment method is to use the Lego to push the spaghetti with an extremely small velocity and with 6 experiments set up. And the data analysis is they have many data analysis, but with some of them, like the curvature increase, the bridge length will increase, etc. And conclusion is like they have like the exact speed will depends on the length of the natural length of the spaghetti and its humidity. And there are pros and cons from the report for the reporter. First, they have a clear experimental setup and pure demonstration, and a thorough experiment consideration. But their cons is they are lacking an assumption. Okay. And I think we can skip to the question. So, you have said that you consider the pushing side, relay side of your initials.
Yes, we see a video. So I think use this feature and explain you. And we made a spaghetti. The front of it is it is close to outer wall, inner wall, and outer wall. And I'll see another experiment. Like this. Outer wall, inner wall, outer wall.
So is relay side one of your variable?
No?
Is relay side one of your variable?
No, I consist my method to push in the spaghetti, so it's not a variable of my experiment.
Because in my observation, I saw that the relay side is different than the mechanism. So I think it's a point to consider. Personally.
But we consist. So.
I mean the mechanism is kind of different.
Oh, okay.
And for the humidity part, so you sink the spaghetti into water for 10 seconds.
Yes.
Sorry, how many different time duration that you have experienced?
Oh, no, I just do put water in water for 10 seconds.
Like only, what, 10 seconds?
Yes.
Not like 10 seconds?
No.
Okay. Because I think if you only sink for 10 seconds, I think the humidity is only for the outside, because spaghetti, is a very thick material, so the inside part will not be really influenced by this. I think personally, have you considered like put in an outer environment for like 1 day and will absorb the water?
Oh, I actually put a spaghetti in water 1 day and
1 day.
1 day.
Okay.
And it initially becomes so soft.
Yeah.
So it even cannot be pushed into the
Oh, I mean
aspiration.
put this like in the outside environment, like not sinking into the water, so like explore the air.
The point is to prove that humidity matters, or it's not about what is saying.
I mean the humidity might not be very thorough to the whole spaghetti. Like it might be only like the surface.
Oh, yes.
Like if you sink it only for 10 seconds. Have you considering the
No, I'm not considering in different experiments.
And can you turn to page 33? what's the length?
Length.
Yeah.
Oh, it's natural.
Oh, so the conclusion is like the natural length increase, the velocity will decrease.
And this is because this is because the airplane is consistent. So the natural length decrease, the velocity will increase.
Have you considered the collision violation?
What?
The collision. Like the fracture while you push it. Before the spaghetti have break inside the tube.
So which
Like if the length increase to a point like too long, then the spaghetti will break even it has successfully entered the tube.
yes.
Have you observed this?
I'm not observing this phenomenon, but we have a success rate to do for this experiment. And the success rate decrease, then that means it fracture. It fracture before the spaghetti eject.
Have you considered if the width of the spaghetti is decreasing?
No, in our experiment, I'm not considering the width of spaghetti.
Then what do you think personally it will have? The result will be if the spaghetti is wider.
And if yours the spaghetti wider and your density will decrease. So according to our theory, low it means density. So if the density decreases, the velocity maybe will decrease. And
Why? I'm sorry. Why the width increase with the density? I thought the density would be the same.
if the density will be the same and the width and the mass of spaghetti will increase, right?
Yeah, like it's a whole material system.
The mass of spaghetti will increase.
Okay.
So the ejection length of spaghetti will increase too, right? The ejection length of spaghetti. So when the ejection length of spaghetti increase, they can be ejected.
But do you think that you have to have a higher force?
And when we do this before, if we have a bigger force, and it will fracture before the spaghetti ejection.
If the spaghetti totally fill the tube, do you think it will also eject? Like totally fit the tube?
Totally clear to actually I think we will not. You will not. Because if the spaghetti is totally fitted too, and you don't have the space to have this moment and one now it's bent and eject. You don't have the space to give the kinetic energy to make it eject.
So you think you have to have collision to make a spaghetti?
Sorry, do you request it?
So do you mean that you have to have collision with the tube that the spaghetti will eject?
What? No. And can you repeat your question?
No, you mean that if it fits the tube, it cannot eject. So you mean it has to have the space to collide with the tube, then the spaghetti will eject.
You need the space to let it fracture.
Can you explain your theory and experiment difference? The theory and experimental difference.
Oh, I do that. Yes. Yes, for sure. I revised my theory according to our experiment. Is this good?
Yeah, can you explain it?
Oh, because you can see in the second and the third experiment, the slope were different, right? And we hypothesize that the slope is because the energy conversion due to the buckling. And as you can see, if our theory is right, the velocity will proportional to the square root of air pump, right? Reciprocal air pump. But you have an intercept. So I hypothesize that the G means the energy loss and substitute to the velocity, and it can also mean the velocity loss. And combined buckling explain the boundary condition operator.
And so, what do you think that caused this?
What?
It's okay. Have you analyzed the internal pressure of the spaghetti?
Internal pressure.
Like how the spaghetti bear the pressure?
No.
The dynamics inside the internal spaghetti.
I'm not discuss about it. I'm not discuss about it.
Your results shows that it is linear between E and force. How can you use linear theory in page
13. And can you repeat your question?
I've asked that your results show that it isn't linear between E and force in the experimental model. And how can you use linear theory in page 13?
We just compare the humidity. There are some effects between the E, and because we just
Humanity? Sorry, I didn't hear. Humanity?
your question is humidity, right?
Okay.
Okay. So, and because we just throw the spaghetti into the water 10 seconds, so we don't have enough data to verify the E operation between the people.
And have you considered the weather influence? Since you have mentioned that its humanity will affect the rate of the spaghetti. So if it's rainy day that is more humid, do you think that would change your result?
And we trust it's fixed. And we also, and according to our experiment data, and we also can see and because our lab has an air conditioner, so there have some so strong effects about the spaghetti. And as you can see, they have a linear correlation. So I think I do many times experiment to ignore this effect.
So have you measured that the humanity is all the same all the time?
I'm not measuring, but I will think it is consistent.
But in my point of view, I think since the humanity is one of your variables, so I think the humanity and the environment should be considered. Can you explain why some error bar is very big?
Oh, this is because an R force is a possibility function. The R force is a probabilistic function. So there are some error bar, and it explains the probability function. It explains the error bar. No, not this. It explains the error bar here. It is because it presents fracture, not buckle, so it will have a linear correlation.
And then since stress is a probabilistic function, have you considered using a simulation software to simulate the experiment?
Simulate. All similar result is this picture.
Like using the internal stress simulation.
Okay, time is up. The opponent, please summarize the discussion in 1 minute.
Okay, so we have discussed about why the error was big, and they have said that because the stress is a probabilistic phenomenon, and that they didn't consider the humanity and the environment, but the opponent think that since the humanity is important variables, we need to consider the humanity and the environment. And they have considered the revised side of the initial condition of pushing the spaghetti, and they have standardized the revised side. But in the opponent's point of view, we think that the revised side is a very important variable too, since it will have a totally different mechanism inside it. in their experiment 2 or 1, they didn't consider the internal humidity of the spaghetti. So the opponent think that the humidity might only be at the surface.
Okay, the reviewer has 3 minutes to ask the question.
Okay. To the reporter, do you think the effect of maximum deformation, do you think the maximum deformation affects the spaghetti breaking length? It means that does the spaghetti always break in the same curvature radius?
No.
How about the does the spaghetti always break in the same curvature radius in different experiments? Yes, it's like
Do you mean that the spaghetti?
how does it bend? Yes,
Like
like the. Do you think
So the variable is the radius
of the spaghetti is like it's all the? Okay, thank you. Is there a critical radius when the spaghetti releases in the maximum energy upon fracture?
Can you rephrase the question?
Okay. Is there a critical radius when the spaghetti releases the maximum energy upon pressure? It means is there a point that the energy loss is the minimum? Do you think you can predict where is it? Like the
I'm not good at it because, but we can use our instrument to predict it.
can you predict? How about the opponent? Like in which conditions that the energy loss of the
I think the contact area is very variable since the contact area is the friction. So the friction is the main energy loss.
when the friction is the
Smaller.
minimum,
Yeah.
then the okay.
Oh, okay. And as you can see, we compare the different ways and the different and if you make the line to here and make it to here, then they are not the same intercept. And we can use this picture to predict the.
Okay, I understand. Okay, can the reporter ensure the material of the spaghetti is uniform? Do you measure that? Like the material of the spaghetti, is it uniform?
Yes.
Okay. Do you think that it might be not uniform or another like other conditions?
Personally, in my experiment, if the spaghetti exploded the environment, it will absorb the water.
Okay.
So it will be soft.
What do you think is the main factors that causes the energy loss? Because you mentioned a G in your experiment. What do you think the main reason is?
The main reason
is of the.
it's about energy loss
Like
because the
oh.
pressure friction.
Okay. How about the comment?
Okay,
About the
time is up. 2 minutes preparation time for the review. Okay, the reviewer take the floor.
Honorable juries and fellow competitors, I'm the reviewer from Team Excelsior. Today I'm going to review problem number 13. So here's the problem statement. Today I'll mainly focus on why will the spaghetti will eject at a surprisingly high speed and what parameter will affect the launching speed. So this is a review of the reporter. The theory they use, they mentioned the buckling and the fracturing theory, and they compared them together. And they also measure the Young's modulus and the linear elastic theory. And for the experiment, they have 5 experiments, which is like the radius of curvature, the tube thickness, the humanity, the length of the spaghetti, and the curve angle. And however, I would like to talk about the weakness and the strengths of the reporter. They did well on providing a clear observation video, and they explain the phenomenon well, and they provide 2 theories that could explain the experimental data. But however, the reporter didn't do well on, they didn't control the pushing force, and they didn't explain the direction of the friction completely, and also they didn't analyze the deviations. And the review of the opposition, they did well on noticing the lack of the analyzing, comparing the theory and the parameters, and however, they didn't discuss the boundary conditions, and they didn't notice the lack of explanation about deviations. And these are the quick questions about their discussion. So the opponent asked, did other time durations of soaking the spaghetti? And the reporter said no. But the reviewer agrees with the opponent that we suggest the reporter to do more experiments to analyze, so we can know if the effect of this humanity is linear or not. And then is another key discussion about radius of the tube. The opponent asks if the space of the tube is the same as the spaghetti, will the spaghetti still eject? And the reporter said no. However, we does not agree with the reporter because we think the space of the tube does not affect the breaking condition of the spaghetti. And then is the simulation. The opponent asks if the reporter used the simulation stopper to simulate the experiment, and the reporter said yes, and we agree with the reporter. And these are our questions. This is about the tube radius. So we asked if does the tube radius affect the maximum deformation of the spaghetti. The opponent and the reporter they think it's not. And for another question is about the boundary limit. We asked if there is a critical radius, and the opponent think that the content area is important. The reporter can say they can recreate in the experiment. And here's about the point mix. They failed to discuss about the effects of Young's modulus due to they didn't do a lot of experiment points, and also did not discuss the changing of the 2 parameters in the humanity experiment, and they didn't explain the boundary condition and the weather condition. And also they didn't explain the reason of energy loss. We didn't hear it in the discussion, and the opponent and the reporter didn't discuss about error analysis.
Okay, thank you.
And as a reporter, we clarify the purpose of the last experiment, and the place is a Paris force. The size will push the spaghetti and the energy loss, and the spaghetti is uniform, and the curvature of the maximum ejecting velocity. And now is Riveton. We discussed about the humidity and the width of spaghetti. And now this is Andrew. And liaison disclaimer, the opponent underscore the correlation, which is not the main focus of the opponent. And main focus is about friction and the buckling. And the opponent seems to fail to understand the function of air conditioning. Our humidity is fixed. And opponent claims that the mechanism of different size of tube wall is different. nonetheless, they didn't discuss that there was a which is confusing. And opponent mentioned the internal stretch, which we didn't manifest in our presentation. And nevertheless, the opponent didn't discuss the further reviewer consider we are lack of deviation analysis, which we have mentioned. And we actually do the width of the experiment. So the reviewer says we didn't consider the tube width. So I do the experiment. And now this is my summary. Thank you.
Okay. Hutchins Burnley Jr.
I ask, when you say humidity, are you talking about the humidity in the environment or the moisture in the spaghetti sample? Your answer is humidity. What do you mean? I seem to be confused.
Our experiment is about spaghetti.
When you answer a question about humidity, what humidity are you referring to?
Moisture of spaghetti.
Moisture. Are you the same?
Yes, but
You?
yeah.
Okay. But, yeah. But in your theory, does moisture enter into your formula?
Yes, the E.
No, that's Young's modulus. You don't call that moisture. E. Big E, right? That's my question. The moisture, or the humidity, anyway, moisture, its effect should be reflected in change of Young's modulus, right?
Yes, the humidity will not, it's not affect the Young's modulus. Well,
Is it?
the moisture will affect the Young's modulus.
Yeah, it will. So all the discussion about moisture, what's the point? We just mentioned, you only hear about the last modulus, the Young's modulus, right? Which you measure. Did you measure?
No.
You didn't.
I just do for humidity for 1 day, so you don't have enough data to prove the.
Well, I thought you should make your formula use Young's modulus, you naturally have measure, right?
Yes,
You have.
I measure it Young's
Yeah,
modulus.
Okay. If not other question, I will come on.
Is there any?
No, I didn't see, I saw you, one of the slides gave reference about the fracture theory. No, you don't have to, I'm just, now, you presumably you use others' theories, right? Either the buckling or the fracture you use. Now, what are your major contributions in this part? In theory, the experiment, of course, we did.
Oh, fracture. I may talk about fracture.
No, your contribution. I'm sort of concerned about your contribution.
Oh, my contribution is to simulate
So
this
so
distribution.
probably you don't have much contribution. Sorry.
Okay, I have the same question with the Professor Chai, because you say you use the spaghetti in the soaking your treatment, right? Because your spaghetti wet or dry. Yes. And in my opinion, because you didn't have give the definition of the spaghetti about the wet spaghetti, because you soak it in the water or maybe juice, okay, I don't know, okay, for 10 seconds, right? But the dry spaghetti and the wet spaghetti different. So how to definition of the change in your experience about the spaghetti? You know, because in this experiment, the row is different. One is dry spaghetti, and the other is wet spaghetti. So they are different. So of course you can do the experiment, but how to differentiate to the change of your spaghetti? Just 10 seconds, or because one is the spaghetti and one is spaghetti with water.
We didn't quantify it.
Okay. Okay. Another question. So suppose you can do this experiment again. How to give it a new definition?
Maybe I think I will soak spaghetti into the water and calculate the EI modulus again, and we can compare the difference between these two.
Okay. Or you can use the spaghetti and the weight before soaking, right? Okay. And after. I think. Okay. So how about opponent and okay. Sorry, time out. Sorry.
Come to the scoring time for the Q. Ready? Okay, for the reporter. 8, 9, 8, 7, 7. For the opponent, 7, 8, 7, 6, 5. For the reviewer, 8, 8, 7, 6, 5. Okay, let's take a 10-minute break.